So for question 3 of part B, we're going to find the parametric and symmetric equations of the line passing through the point 1, 1, 2 that is perpendicular to both I plus j hat and j hat plus k hat. So to begin, we know that when we take the cross product of two vectors, we get a perpendicular vector or a normal vector. So what we want is a vector that's perpendicular to both I plus j and j plus k. So our vector, which I'm going to call v, is equal to I hat plus j hat cross j hat plus k hat. So we know that I hat is equal to 1, 0, 0, j is equal to 0, 1, 0, and k hat would be 0, 0, 1. So we know I plus j hat would be equal to the vector 1, 1, 0, and j hat plus k hat would be equal to 0, 1, 1. So now to get v vector, we're going to cross these two. So our v vector would be equal to the cross product ij k hat form, and we got 1, 1, 0, 0, 1, 1. So solving for the I component, we got 1, 0, 1, 1 minus the j hat component, 1, 0, 0, 1 plus the k hat component, 1, 1, 0, 1. So now doing the actual cross part, 1 times 1 is 1, 1 times 0 is 0. Subtract them, we get just a positive I, positive 1, 1i. Doing the same thing this way, 1 times 1 is 1, 0 times 0 is 0. Subtract that, we get a positive 1, but we have this negative sign here, so it's minus 1j. Same thing for the k, we got 1 times 1 is 1, 1 times 0 is 0. Subtract them, we get 1. We have a positive k, so it's plus k. So our v vector would now be the coefficients of these components, which is 1, negative 1, 1. Now we have a perpendicular vector to both I plus j and j plus k. So our equation of a line to find parametric and symmetric equations in standard form would be r is equal to r naught plus t v, where v we just found, which is our perpendicular vector, or in this case it's going to be parallel, and I'll explain why. And then we have r naught, which is our point that's passing through. So graphically, we have some equation of a line. Let's call it like this, or make it thinner, right? And we have r naught, which is a vector that is a point on the line, so it's pointing to some sort of generic point on the line. And then we have our plus t, where t is just a constant coefficient saying how big our line is going to be. And v is a vector that is perpendicular to I plus j and j plus k, but it's also parallel to this line, because this line is perpendicular to also perpendicular to I plus j and j plus k. So that means v would be parallel to this line. So if I added plus tv, we would, if it was a positive t value, it would be somewhere this way. If it was a negative t value, it would be somewhere this way. And depending on how big the t value is, it could go all the way out this way. Or how small, how negative it is, it could go all the way out this way. And we can see that it is on a line. So that is why this is our equation of the line. So filling in what we know, our point 1, 1, 2, we're going to write in vector form for r naught, 1, 1, 2, plus t times our vector that we found right here, 1, negative 1, 1. So if I distribute that t, we get vector t, negative t, positive t, And now we're just adding components. So for our x, this is our x component, x, y, z. So x would be equal to 1 plus t. Similarly, we have y, which is equal to 1 plus a negative t is just minus t. And then we have our z, which is equal to 2 plus a positive t, 2 plus t. And these, all these x, y, and z is our parametric equation. Now just to find symmetric equation, all we have to do is solve for t. And in this case, all the t values are going to be the same, so I can set them all equal to each other. So for the x part, I could subtract the 1 to get a t equals x minus 1. So solving the t for y equals 1 minus t, I could add the t to both sides and then subtract the y, so t equals 1 minus y, which is the same t here. So all these equal each other, so 1 minus y. And then z, same thing for z, I could subtract the 2. So z is equal to, z minus 2 is equal to t also, which I already wrote. So these would be our symmetric equations. And that's how you find that.